Here we are again, and today we are going to talk about the concept of a normal force. A normal force. So here's a definition that you can use to think of what a normal force might be. What it is it's a reaction force maybe I'm going to change that to the reaction force, just so the grammar works out. It's the reaction force of a surface. Normal forces always involve a surface of some kind. The reaction force of a surface when an action force is applied to it. So if we think about this in terms of Newton's laws, this is Newton's third law in action. If a force is applied to a surface, then the surface pushes back. And it pushes back with an equal and opposite force. So this is basically an example of Newton's third law in action. So you might want to go back and reread the third law. Basically what it says is that surfaces can push back. Of course, they never push on their own. Surfaces don't just suddenly push things into the air. They only react to, they're a reaction force. They only react to a different force, an action force of some kind. And those action forces could be all kinds of things, as we will see. So, surfaces push back, Newton's third law. So let's do a very simple example, a picture sort of, or a scenario, where we can get our head around what this normal force might be. Let's think about a box that is 20 kilograms, and let's say it's sitting on the ground or a table or some sort of surface of any kind. Let's try to imagine the forces that might be acting on this box. We know, of course, that our friend, the force of gravity, pulls downwards on the box. So we can call that Fg. And in our last lesson, we learned that Fg can be calculated as mg. So 20 times 9.8. So we now know exactly how much this gravity force is pulling with. It would be pulling with 196 newtons downward gravity force. Now we think of Newton's laws. At first we might say that's it, there's no other forces. But there is, because if there were no other forces, we would clearly see a net force pulling down on this block, which would mean the block must accelerate. F equals ma, Newton's second law. Since the block is not accelerating, that means that the forces must somehow be balanced. So there must be another force that we're not seeing. And that other force is the ground pushing back against the gravity that's trying to pull the block up, or pull the block down, sorry. So the ground pushing up is what we call the normal force. I'm going to call it Fn, the normal force. Now, the normal force could be any kind of force in disguise, okay? But usually, what it is it's the electromagnetic repulsion of the electrons on the bottom of the block and the electrons on the ground. When they get really close to each other, what looks like to us touching, they're actually pushing against each other, and they're creating the ability of things to push. So the ground is pushing back against gravity. Now, the next question would be, okay, if that's the force that's balancing the gravity, how much is it? And in a simple case like this, you could use Newton's law and you could say, well, if it's 196 down, then the ground must be pushing with 196 up in order for it to be balanced. And that would be correct. However, I'm going to show you a more sophisticated way of determining the normal force, because you can't always rely on that unless you have a very simple situation. And of course, in physics, nothing is simple. So a better way to evaluate how much a normal force might be is to look at the net force equation, F net. Now you can look at the F net x or the F net y. Normal forces can occur horizontally or vertically. So you have to look at your picture to decide which kind you have. Here, of course, we have a vertical one. So F net y is where the normal force will be found. Now remember, F net is the sum of all the vertical forces, all the uppy downy arrows. And I seem to have two of them in my picture, so I'll write them in. There they are. Then we realize, using Newton's laws, that F net must be equal to ma, Newton's second law. And of course, the force of gravity, I know that number. It's 196 newtons. And it's down. And since the math cannot see my picture, I need to tell the math that that number is down by using a negative sign. And then, of course, the normal force is what I'm actually trying to figure out, so I'll leave that one blank. Now let's look at this MA here on the left side. We looked at this block sitting still on the surface, on the ground. If it's sitting still, its velocity is not changing, which means there's no acceleration. Which means if there's no acceleration, then A is a 0. Which means that this whole thing is 0. The net force is 0, and we know that because when forces are balanced, net force is 0. So we can make that little addition to our equation, and then it becomes clear if you move the 196 to the other side, that is the value of the normal force, 196, and of course that would be newtons. Don't confuse the N for newtons with the N for normal, right? In fact, I shouldn't have written it that way, because that's precisely what it's going to do. It's going to confuse you. So let me just put the 196 with the proper N right up here, newtons there. That makes better sense. Now again, you could look at the picture and you could tell that just by looking, that if there's 196 down, the normal must be 196 up. But I want to practice this method for when things get more complicated. All right, so that's the normal force. We say that if gravity is trying to pull the block down through the ground, then the ground is pushing back with a force equal to the gravity. Now, the interesting thing about normal forces is there's two important things that they do, two little stars. One, the normal force is always, and this is why it's called the normal force, the normal force always acts perpendicular to the surface that it's acting from. Surfaces can only push straight up or straight sideways. In other words, perpendicular to themselves. They can't push on weird angles. Normal forces always act, I guess that should just say act, always act perpendicular to the surface that is causing them. So if we look at our picture, you can see here that this green line is perpendicular 90 degrees to the surface or the ground. They always have to be that way because that's the way surfaces push. In fact, the word normal in math actually means perpendicular. It's an older word that isn't used as much, but the word normal actually means perpendicular. So that's why it's called the normal force. It has nothing to do with its psychological state. It's not a crazy force or normal force. It's normal meaning perpendicular. The second important thing that happens with normal forces is that they are reaction forces, which means they only push as hard as they have to balance forces. They only push as hard as they have to. They never push more than they need to, even if they could. Let me give you a picture to help explain that. I'll take two boxes, and I'll put one with 20 kilograms, and I'll put another one that's much bigger, 200 kilograms. If we consider the force of gravity that pulls on these two boxes, we already know this one, it's 196 newtons, because we did that up above. While this one, being 10 times larger, will produce, if you do Fg equals mg, 1960 newtons. So the gravity is pulling much harder on this one. The normal force, though, for this block, has to balance the gravity. So in this case, it would be 196 newtons. But over here, the ground is capable of pushing with much more. In fact, here the ground can easily match the action force of gravity and push back with 1,960 newtons. But you'll notice that the ground doesn't push with this force over here on this picture because it doesn't have to. If it did, the box would go flying off the ground, and of course we don't see that in reality. So reaction force. Normal forces are reactions. They only push as much as they have to balance the forces, never more. Okay, let's look at another example of normal force and how we would figure it out. Let's take our box, which is 20 kilograms, the very same one, but let's add another force into the picture. Let's add somebody pulling on this sideways with a force of 40 newtons, which was not the case before. Now let's also draw in our force of gravity. And now we know that there's another force called the normal force, which would be going up against gravity, the ground pushing back. Now the gravity force we figured out. It's mg 20 times 9.8, or 196 newtons. Okay, that's the same as before. But I wonder now if the normal force might be different because we have this additional sideways arrow. Well, the point of this is for you to remember that vertical forces have no effect on horizontal forces, and vice versa. So this 40 newtons, because it's all horizontal, it has no effect on uppy-downy forces. So when I do my F net Y, as I did before, that 40 newtons isn't going to be invited to this party. It is not part of the Y picture. It's part of the F net X, but that's not where the normal force happens to be here. So when I do this, this will again be zero, because even though the block might slide sideways, it will certainly not move upwards or downwards. Its velocity up and down vertically will stay at zero. It will accelerate to the right, but that's not part of F net Y, and that has no effect on the vertical forces. So the normal force will end up being the exact same, right? And you notice how I switched these in order? Remember, the order doesn't matter when you're doing net force, because you're adding them all up. This will still work out to the very same thing, and we get the normal force unchanged, because horizontal forces cannot affect vertical forces. So that's an important thing to remember. Now let's try to imagine a situation that might actually affect the normal, and that would be if you took your block, 20 kilograms, same thing, but this time you didn't pull horizontally, but you pulled on an angle. This is what we often do because humans are kind of tall. And when we pull things with strings and ropes, like a sled or something, there often is an angle when we pull. Let's give that angle an amount, 30 degrees, so we can use it. But let's keep it the same 40 newtons as before. Let's not change that. Now let's add in our gravity force, which we know is going to occur, and mg, which is m times 9.8, it's still 196 newtons. That doesn't change. And now we know there will be a normal force that's pushing up. But because my 40 newton force is on an angle, it has uppy-downy and lefty-righty parts. It has both horizontal and vertical components. So this is the horizontal component, and this is the vertical component. You can see how it has an uppy-downy part that's going to have to be invited to the F net Y party. It's going to have to show up in that equation. Let's calculate it. We remember how to do this. This would be 40 times the sine of 30 degrees. Sine 30 is a half, so this would work out to 20. And this side over here, which we're not going to really use right now, but we will later, 40, whoops, cos, my mistake. This one would be the adjacent side, 40 cos 30. All right, and its value will come out to probably somewhere around 35-ish. Let's just put that down there because we're not really interested in that right now. Now watch what happens when I do my F net Y to find out about my normal. I do have gravity, and I do have a normal force that are vertical, but now I also have this extra upward force, which is a part of the 40 newtons. So I'm going to call that the applied force. We always call the pulling force applied force for some reason. And then that would be the vertical component, or the y part of it. The x part of it, the 35, doesn't show up in here because that's a sideways force, right? Horizontal force, no effect. Now, we still know, however, that the block is not going to accelerate up or down. It can't, because this lifting force over here that you're applying of 20 newtons is nowhere near enough to lift this. You'd need 196 newtons to beat gravity and lift it up. And of course, the ground isn't going to give extra force. The ground is only going to push as much as it has to. So you could never lift something unless you are applying a force, an applied force, that is bigger than its weight, 196. So I can still safely say that this block will not accelerate vertically, up or down, which means the net force vertically will be 0. And I have a gravity force of down 196. And now I'm looking for the normal, but now I must add an additional force of up 20 newtons because of the pulling on an angle. It's an additional uppy-downy force. And of course, that means that this would become, if you group the like terms, minus 176 plus Fn. And when you move it to the other side, you would see that Fn is 176 newtons instead of 196. The ground is actually pushing less. And if we think about Newton's laws, that makes sense. In the first example, we were not helping in a vertical way. Our force was only horizontal. So the ground had to do all the work. The ground had to cover this 196 completely, and the normal force of the ground pushing back was 196. But in the second scenario, by pulling upwards slightly, we added 20 newtons of help to the ground, and the ground said, oh, thank you so much. Now I can work a little bit less since you're helping me out. And I only need to push up with 176. So that combined, together, both you and the ground have canceled out the gravity. You have balanced the gravity force and kept the y net force 0. So sometimes the normal force is not equal to the gravity. A lot of students get into the habit of thinking that the normal force will always be equal to gravity. Because in simple cases, like the first one, it is. Gravity, 196, normal, 196. But in more complex cases, the normal can take on different values, and the only way to really find out is to use this equation, the F net y equation. Okay, and so one more thing to show you, another example, just to kind of remind you that normal forces don't have to always be up and down or vertical. They are a lot. In a lot of questions in physics, they are uppy-downy, but they could also be in different directions. Let me give you an example of your refrigerator at home, and I'll draw this fridge magnet that's stuck to the side of it. That's a common example of something you would see. Fridge magnet. Okay, let's look at the forces that might be acting on a fridge magnet. Well, of course, good old gravity acts on everything. So there's gravity pulling down. And we don't need the numbers, we just want to look at the forces. But there's a whole new force here that we haven't really talked about before. There's a magnetic force, right? Magnetism is pulling the magnet into the fridge. So let's call that F mag, the magnetic force. Now let's look at this magnetic force and this horizontal business. It's a horizontal force. It's pulling the magnet into the fridge, which means if that's the only force, the magnet must somehow accelerate into the fridge. Well, that doesn't happen. So somewhere there's a balancing horizontal force. And guess what it will be? It'll be the fridge surface pushing back. And this would be the normal force. It's perpendicular to the surface of the fridge. And it is the force that sort of balances out the magnetic force so that the horizontal, the F net x, would be 0, which keeps the magnet at a constant speed of 0, not moving. And you might also ask, well, okay, that's great for the x and that's balanced, but look at the y, it's not balanced. And so the up and downy forces, what should happen now is the magnet should accelerate down the fridge, but it doesn't. And there is another force that we're about to learn about in the next video, which would be acting up this way, and it would be the force of friction. So the force of friction is coming next. And of course the force of friction is going to be very closely related to the normal force, and we're going to see how that all works. But for now, I just want you to realize that a normal force can also be sideways. It can be horizontal, and it can be reacting to something different than gravity, like a magnetic force in this case. The other thing that can happen, and it will happen in this class later, if you have a hill and a box on a hill, gravity will pull downwards. As always, gravity can only pull down. But we said that the normal force has to be perpendicular to the surface, which means the ground would have to push this way, perpendicular. And that creates a whole new set of problems in how we balance that. But you'll notice now that the normal force is not totally horizontal, and it's not totally vertical. So we'll learn how to deal with this scenario later, after we get the basics down pat. But be aware that normal forces are not always just a little arrow that points straight down and is equal to gravity. That's only the case in a very simple situation like our very first one. So we have lots of different ways of doing it. So to summarize, the normal force is a reaction force of a surface when an action force is applied to it, at the surface pushing back. It's always perpendicular to the surface, and its value can be found by using an F-net equation for the vertical or the horizontal, depending on where the normal force is found. And that's it for that. There'll be practice questions on your assignment, on your worksheet that I handed out a few days ago. The next section will have practice questions on normal forces, and tomorrow we will start looking at the wonderful world of friction.